distance and scale. The same underlying interaction can be gentle around small worlds, intense near dense stars, or stretched and subtle across vast regions of space. In this video, the aim is to explore how gravity works around the universe, not as a single uniform rule, but as something that takes on different expressions in different environments. From planets and moons to stars, galaxies, and the space between them, this is a slow and steady journey through how gravity shapes the universe. There is no rush, and no need to hold everything at once, just a calm exploration of a force that feels simple close to home, and grows quietly more complex the farther out you go. Gravity is usually encountered long before it is ever named. It is present in the way feet meet the ground, in the way objects fall when released, and in the quiet certainty that things tend to stay where they are unless acted upon. There is no obvious sensation announcing its presence, no vibration, no sound, no visible signal. Instead, gravity feels like the default condition of existence, so reliable that it fades into the background of awareness. On Earth, gravity gives weight to the body. It presses gently downward at every moment, providing resistance that muscles learn to work against from the earlier stages of movement. Standing, walking, sitting, lifting, and even resting are all shaped by this steady pull. Because it never switches off, it rarely attracts attention. Like air pressure or the passage of time, gravity becomes noticeable mostly in its absence or when something goes wrong. When an object is dropped, it falls. When a glass slips from a hand, it accelerates downward and breaks on the floor. These events feel obvious and unsurprising, as if they could not happen any other way. Over time, the mind stops questioning them. Gravity becomes not just familiar but expected. It appears uniform, predictable, and unchanging. This sense of constancy is reinforced by everyday experience. Whether indoors or outdoors, whether near sea level or on a modest hill, gravity feels the same. A cup weighs the same in the kitchen as it does in the garden. The body feels no lighter or heavier from one moment to the next. From a human perspective, gravity seems fixed, almost absolute. Yet even on Earth, gravity is not perfectly uniform. Its strength varies slightly depending on location. The pull of gravity is marginally weaker at the equator than at the poles, due to the planet's rotation and its slightly flattened shape. Altitude also plays a role. Gravity is fractionally weaker on a mountain than at sea level, because distance from Earth's center increases. These differences are small, far below the threshold of human sensation, but they are measurable with sensitive instruments. The reason gravity feels so constant is not because it truly is, but because human perception is limited. The variations that exist are subtle enough to be smoothed out by the scale of everyday life. Muscles, bones, and balance systems adapt to the local gravitational environment and treat it as normal. Over time, that normal becomes invisible. Historically, gravity was first understood not as an invisible background condition, but as a force acting between objects. In the late 17th century, Isaac Newton described gravity as a universal attraction between masses. According to this view, every object with mass pulls on every other object with mass. The strength of that pull increases with mass and decreases with distance. This idea provided a powerful explanation for falling objects, planetary motion, and the orbits of moons. Newton's description of gravity was revolutionary because it unified events on Earth with motion in the sky. The same force that causes an apple to fall also keeps the moon in orbit around Earth and governs the paths of planets around the sun. Gravity was no longer just a local phenomenon. It was universal, operating everywhere in the cosmos. For centuries, Newtonian gravity provided accurate predictions for most situations encountered in daily life and astronomy. It explained why objects accelerate downward at a roughly constant rate near Earth's surface. It described why planets follow stable, repeating paths. For practical purposes, it worked extremely well, and it still does in many contexts. However, Newton's gravity also reinforced the idea that gravity behaves the same everywhere. While the equations allowed for variation in strength, the underlying picture suggested a single, consistent rule applied uniformly across space. This reinforced the everyday intuition that gravity is a fixed property of the universe, rather than something that can take on different forms. In reality, the experience of gravity on Earth represents only one local expression of a deeper phenomenon. Earth is a medium-sized rocky planet with a specific mass, radius, and internal structure. Its gravity is strong enough to hold an atmosphere, shape oceans, and anchor life to the surface, but not so strong as to crush structures or prevent movement. This balance feels natural only because life evolved within it. If Earth were slightly more massive, gravity would be stronger. Objects would weigh more, movements would require greater effort, and biological structures might need to be more robust. If Earth were less massive, gravity would be weaker. Objects would fall more slowly, jumps would carry higher arcs, and the atmosphere might be thinner or escape into space. Small changes in planetary mass lead to noticeable changes in gravitational experience. Because Earth provides a stable and narrow range of conditions, it is easy to mistake that local balance for a universal standard. Gravity feels like a constant because it has been constant within the limits of lived experience. But those limits are small when compared to the range of environments found across the universe. Even within the solar system, gravity varies dramatically. The Moon's gravity is much weaker than Earth's, allowing astronauts to lift themselves with ease and objects to fall slowly in graceful arcs. Jupiter's gravity is far stronger, enough to compress matter to extreme densities and dominate the motion of nearby objects. These differences do not require new laws of physics. They emerge naturally from differences in mass and size. The key point is that gravity is not something that simply exists at one strength everywhere. It depends on the properties of the objects involved. Mass, distance, and distribution all matter. The gravity felt on Earth is the result of Earth's particular combination of these factors, not a default setting of the universe. Understanding gravity as a local experience rather than a universal constant opens the door to a broader view. It invites curiosity about how gravity behaves in other places, under other conditions, and at other scales. The familiar downward pull becomes one example among many, rather than the defining case. By starting from what feels obvious and dependable, it becomes possible to gently question those assumptions. Gravity does not change abruptly from place to place, but it does change meaningfully. The version experienced on Earth is not wrong or incomplete, but it is specific. It belongs to this planet at this distance from its center, with this mass beneath the surface. Recognizing that fact does not make gravity less reliable. Instead, it places it in context. Gravity remains one of the most consistent features of the universe, but consistency does not mean uniformity. What feels constant here is part of a much wider pattern, one that stretches far beyond the ground beneath your feet. Gravity is often spoken about as a force, something that pulls objects together across empty space. This description works well enough for many everyday situations, but it is not how gravity is understood at the deepest level. In modern physics, gravity is not treated as a mechanical pull or an invisible tether stretching between objects. Instead, it is understood as a fundamental interaction that emerges from the structure of the universe itself. To see why this distinction matters, it helps to notice how gravity differs from other forces that feel more familiar. When a hand pushes a door, there is contact. When a magnet attracts metal, there is a visible interaction that weakens quickly with distance. Gravity behaves differently. It acts between objects regardless of what lies between them. It cannot be blocked, shielded, or turned off. Its influence extends across vast distances, shaping the motion of planets, stars, and galaxies alike. For a long time, gravity was described using the framework developed by Isaac Newton. In that picture, gravity is a force of attraction between masses. The larger the masses, the stronger the attraction. The farther apart they are, the weaker the pull. This description is simple, intuitive, and remarkably effective. It explains falling objects, planetary orbits, and the predictable motion of moons and comets. Even today, it remains accurate enough for many practical purposes, from engineering to spaceflight planning. However, Newtonian gravity leaves an important question unanswered. It describes how gravity behaves, but not what gravity actually is. It treats gravity as a force acting instantaneously across space, without explaining the mechanism by which that influence travels. As scientific understanding advanced, this limitation became increasingly difficult to ignore. In the early 20th century, Albert Einstein offered a radically different way of thinking about gravity. Rather than treating it as a force acting across space, Einstein described gravity as a consequence of the geometry of spacetime itself. This idea forms the foundation of general relativity, published in 1915, and it remains the most accurate description of gravity currently available. In this view, space and time are not separate backgrounds against which events unfold. They are combined into a single physical structure called spacetime. Spacetime has measurable properties. It can be stretched, compressed, and curved. Mass and energy tell spacetime how to curve, and that curvature tells matter how to move. Under general relativity, objects do not fall because they are pulled by a force. They fall because they are following the straightest possible paths through curved space-time. These paths are called geodesics. To an observer embedded within space-time, this motion appears as acceleration. From the inside, it feels exactly like a force acting downward. This idea can feel abstract at first because curved space-time is not something that can be directly seen or touched. But its effects are measurable and precise. One of the key insights of general relativity is that gravity affects not only motion, but also time itself. Clocks tick at different rates depending on their position in a gravitational field. Time runs slightly slower, closer to massive objects, and slightly faster farther away. This effect has been measured repeatedly using atomic clocks, and must be accounted for in satellite navigation systems to maintain accuracy. The difference between Newtonian gravity and relativistic gravity is not that one is wrong and the other is right. Newton's description is an approximation that works well when gravitational fields are weak and speeds are much slower than the speed of light. General relativity becomes essential when gravity is strong, distances are large, or extreme precision is required. On Earth, the difference between these descriptions is subtle. Everyday experience does not reveal the curvature of space-time. Objects still fall downward, orbits remain stable. The familiar picture of gravity as a force continues to work. This is why gravity feels simple and intuitive at human scales. The deeper structure is hidden beneath effects that are too small to notice directly. Spacetime itself is not a passive stage. It responds dynamically to the presence of mass and energy. A massive object like Earth curves the space-time around it. Objects moving nearby naturally follow paths shaped by that curvature. The Moon follows a curved path around Earth, not because it is being tugged sideways, but because it is moving through a curved space-time geometry created by Earth's mass. An important feature of this picture is that gravity is not something added on top of space. It is built into the shape of space and time themselves. Where space-time is more curved, gravity appears stronger. Where space-time is flatter, gravity appears weaker. This provides a natural explanation for why gravity varies from place to place, without requiring any change in physical laws. This also explains why gravity behaves differently from other forces. There is no gravitational substance flowing between objects. There are no particles carrying gravity in the everyday sense. Instead, there is a continuous geometric structure that governs motion everywhere. Objects respond to that structure simply by existing within it. One way to understand this intuitively is to imagine motion without gravity. In empty, flat space-time, an object moves in a straight line at constant speed. This is the natural state of motion. Gravity changes what counts as a straight line by altering the geometry through which objects move. What appears curved or accelerated to an observer is actually straight motion within a curved space-time. This perspective also clarifies why gravity cannot be switched off. As long as mass and energy exist, space-time will have structure. As long as space-time has structure, motion will be guided by that structure. Gravity is not a feature layered onto the universe. It is woven into its geometry. Importantly, general relativity predicts effects that Newtonian gravity cannot. These include the bending of light around massive objects, known as gravitational lensing, and the precise precession of planetary orbits. These predictions have been confirmed through observation and experiment, reinforcing the idea that gravity is best understood as geometry rather than force. Despite its conceptual depth, this view of gravity does not contradict everyday experience. It explains why gravity feels steady and uniform on Earth, while allowing for dramatic variation elsewhere. Near extremely massive or dense objects, space-time curvature becomes intense, leading to effects that have no Newtonian equivalent. In regions with very little mass, space-time becomes nearly flat, and gravity grows faint. By moving from a force-based picture to a geometric one, gravity becomes something both simpler and more profound. Simpler because it requires no mysterious action at a distance. More profound because it ties together space, time, motion, and mass into a single framework. This shift in understanding replaces an intuitive but incomplete idea with a deeper model that still accounts for everything already known. The sensation of weight, the fall of objects, and the motion of planets all remain exactly as experienced. What changes is the explanation beneath those experiences. Gravity in this view is not something acting within the universe. It is part of what the universe is. Gravity varies because the universe is not uniform. Objects differ in mass, they occupy different positions, and they are separated by different distances. These differences matter. They shape how strongly gravity acts and how that influence is felt from one place to another. What feels steady and unchanging on Earth is the result of very specific conditions that are not repeated everywhere. In its simplest description, gravity depends on two main factors: how much mass is involved and how far apart objects are. More mass produces a stronger gravitational influence. Greater distance weakens that influence. This idea appears clearly in Newtonian gravity, where the strength of gravity increases with mass, and decreases rapidly as distance grows. While the deeper explanation of gravity comes from curved spacetime, this relationship between mass, distance, and strength remains valid and observable. On Earth, distance from the planet's center changes very little during everyday movement. Standing up, sitting down, or walking across a room alters that distance by only a tiny fraction. Because the mass of Earth is large and the variation in distance is small, gravity feels constant. The changes are too subtle to notice without instruments designed specifically to detect them. As distance increases, however, gravity weakens. This weakening does not happen abruptly. Gravity does not switch off beyond a certain point. Instead, it fades gradually, becoming less influential the farther away an object moves. The pull never fully disappears, but it becomes increasingly difficult to detect as distance grows. The Moon provides a useful example. Earth's gravity is strong enough to keep the Moon in orbit, even though the Moon is hundreds of thousands of kilometers away. At that distance, Earth's gravitational influence is weaker than it is at the surface, but it is still strong enough to guide the Moon's motion. The Moon, in turn, exerts its own gravitational influence on Earth, producing tides in the oceans. This mutual interaction shows that gravity extends far beyond the surfaces of objects and operates across empty space. Move farther still, and Earth's gravitational influence continues to weaken. At the distance of the Sun, Earth's gravity is negligible compared to the Sun's. The Sun's mass is so much greater that it dominates the motion of planets, asteroids, and comets throughout the solar system. Earth becomes just one contributor among many, its gravitational role reduced by distance and by comparison with a far more massive object. This pattern repeats throughout the universe. Small bodies like asteroids exert only weak gravitational influence. Planets exert more. Stars exert much more. Entire galaxies containing billions of stars produce gravitational effects that shape vast regions of space. At each step, mass and distance work together to determine how gravity behaves. It is important to understand that gravity weakens smoothly rather than fading in steps. There is no boundary where gravity suddenly ends. Even objects separated by immense distances still exert some gravitational influence on one another. The effect may be so small that it has no practical consequence, but it is never truly zero. This gradual fading is one reason gravity can be difficult to conceptualize. Human intuition often expects forces to have clear limits. Pushes and pulls usually stop when contact ends. Gravity does not behave that way. Its influence stretches outward indefinitely, thinning with distance but never vanishing completely. To describe this extended influence, physicists use the concept of a gravitational field. Gravitational field is not a physical substance filling space. It is a way of describing how gravity acts throughout a region. At every point in space, the gravitational field has a certain strength and direction, determined by the mass and distribution of nearby objects. Thinking in terms of gravitational fields helps clarify why gravity varies. Near a massive object, the gravitational field is strong. Far away, it is weak. Where multiple masses are present, their fields overlap and combine, creating complex patterns of influence. The gravity experienced at any location is the result of all relevant fields acting together. On Earth's surface, the gravitational field is dominated by Earth's mass. Contributions from the Moon, the Sun, and distant planets are present but small. They add subtle variations detectable with sensitive measurements but not noticeable in daily life. This dominance creates the impression that gravity is simple and singular. As environments change, so does the balance of gravitational fields. On the Moon, Earth's gravitational field competes with the Moon's own weaker field. In deep space, far from large bodies, gravitational fields become faint and diffuse. Motion there is governed by whichever mass exerts the greatest influence, even if that influence is small. From a relativistic perspective, this variation reflects changes in spacetime curvature. Mass and energy curve spacetime, and that curvature becomes gentler with distance. Close to a massive object, spacetime is more strongly curved, guiding motion sharply. Far away, spacetime flattens and paths straighten out. The transition is smooth, continuous and predictable. This explains why gravity cannot be uniform across the universe. The universe contains objects of vastly different masses, arranged in complex patterns. There is no single gravitational environment that applies everywhere. Each location has its own balance of influences, shaped by nearby matter and energy. Even within a single planetary system, gravity varies dramatically. The surface of a rocky planet, the upper atmosphere of a gas giant, and the space between planets all present different gravitational conditions. These differences affect how matter behaves, how objects move, and how structures form over time. One quiet implication of this is that gravity is always local. It is shaped by what is nearby, and by how far away those influences are. The gravity experienced at any point is not a universal constant imposed from outside. It is the result of the surrounding universe acting through mass, distance, and geometry. This locality helps explain why gravity feels so dependable, while also being so variable. In any given place, the gravitational environment changes slowly. Large masses move on long timescales. Distances shift gradually. As a result, gravity appears stable within a local frame of reference, even though it differs widely from one region to another. Understanding gravity as something that varies with mass and distance provides a bridge between familiar experience and the wider universe. It shows that the steady pull felt on Earth is not an exception or a rule, but one outcome among many. The same principles apply everywhere, but their effects depend on where and what you are. Gravity does not behave differently because the laws change. It behaves differently because the universe is not the same everywhere. Within a single solar system, gravity already shows a remarkable range of behavior. The same physical principles apply everywhere, but the experience of gravity changes from world to world in ways that are immediate and tangible. By comparing a few familiar destinations, it becomes clear that gravity is shaped not just by size, but by deeper properties such as density, composition, and internal structure. On Earth, surface gravity provides the baseline for nearly all human intuition. Objects fall at a steady pace. Bodies have weight that feels neither crushing nor negligible. The planet's mass and radius combine to produce a surface gravity that life has adapted to over billions of years. Muscles, bones, circulation, and balance systems are all tuned to this particular gravitational environment, making it feel natural and unremarkable. The Moon offers the first clear contrast. With far less mass than Earth and a smaller radius, its surface gravity is much weaker. An object that weighs 100 kilograms on Earth would weigh roughly 16 kilograms on the Moon. Astronauts visiting the lunar surface experienced this difference immediately. Movements became slow and floating. Simple steps turned into bounding arcs. Objects dropped from hand height took noticeably longer to reach the ground. This reduced gravity does not come from the Moon being small alone. It also reflects its internal structure. The Moon is less dense than Earth, with a smaller metallic core and a simpler geological history. Less mass packed into a smaller volume produces a weaker gravitational field at the surface. The result is a world where gravity is gentle enough to reshape motion without eliminating it entirely. Mars provides a different variation. Larger than the Moon but smaller than Earth, Mars has a surface gravity that sits between the two. A person standing on Mars would weigh a little over 1/3 of their Earth weight. This difference is large enough to affect movement and long-term health, but not so extreme as to make walking unfamiliar. Mars also illustrates how composition matters. Despite being larger than the Moon, Mars has lower density than Earth. Its core is smaller relative to its size, and its overall mass is lower than its diameter alone might suggest. As a result, surface gravity remains modest. Data gathered by NASA missions such as the Viking landers, the Mars exploration rovers, and the Curiosity and Perseverance rovers have helped refine measurements of Martian gravity and confirm how closely it matches theoretical predictions. Standing on Mars would feel lighter but still grounded. Objects would fall more slowly, jumps would carry higher and longer. Over time, the body would adjust to the reduced load on bones and muscles. These changes are not hypothetical. Studies of astronauts aboard space stations combined with robotic mission data help scientists understand how gravity influences physiology and movement. The gas giants introduce a more counterintuitive case. Jupiter, the largest planet in the solar system, has a surface gravity stronger than Earth's, despite having no solid surface in the traditional sense. At the level of its cloud tops, gravity is more than twice as strong as Earth's. A person somehow supported there would feel significantly heavier, even though Jupiter is made mostly of hydrogen and helium. This stronger gravity comes from Jupiter's immense mass. Although its density is lower than Earth's, its sheer size means that enormous amounts of material are packed into a vast volume. The result is a powerful gravitational field extending far into space. Jupiter's gravity dominates the solar system after the Sun, shaping the orbits of moons, asteroids, and even influencing comet paths. Saturn, despite being nearly as large as Jupiter, has lower surface gravity. Its density is much lower, meaning less mass is concentrated within its radius. This comparison highlights an important point. Size alone does not determine surface gravity. Density and mass distribution are equally important. A larger planet can exert weaker gravity if its material is spread more thinly. These planetary differences explain why standing on different worlds would feel radically different. On the Moon, the body would feel light and buoyant. On Mars, movement would feel easier, but still familiar. Near Jupiter's cloud tops, weight would increase dramatically, making even small motions more demanding. None of these experiences require changes to physical laws. They arise naturally from how mass is arranged. NASA's planetary missions have played a key role in confirming these differences. Tracking spacecraft trajectories, measuring orbital speeds, and analyzing lander data allow scientists to map gravitational fields with high precision. Missions such as Juno around Jupiter and Lunar Reconnaissance, Orbiter around the Moon, have revealed subtle variations caused by internal structures, mountain ranges, and hidden mass concentrations. These measurements show that gravity is not perfectly uniform even across a single planet. Variations in crust density, underground structures, and geological history all contribute to small local differences. On Earth, these differences are used to study tectonic activity and resource distribution. On other planets, they reveal information about formation and evolution. What emerges from these comparisons is a clear pattern. Surface gravity depends on the balance between mass and radius, shaped by composition and internal structure. Two planets of similar size can feel very different. Two planets with similar gravity can have very different appearances. Gravity is sensitive to what lies beneath the surface as much as to what is visible from space. These planetary examples bring abstract ideas into physical terms. Gravity is no longer just a concept tied to equations or space-time curvature. It becomes something that can be felt, measured, and compared. The solar system becomes a natural laboratory where gravity reveals its variability without leaving home. By examining neighboring worlds, gravity stops being a single familiar sensation and becomes a spectrum of experiences. Each planet represents a different outcome of the same underlying principles. Together, they show that even within one star's reach, gravity has many expressions, each shaped by the history and makeup of the world beneath it. Stars appear calm from a distance. They rise and set, shine steadily, and seem unchanged across human lifetimes. Beneath that steady light, however, gravity is at work in a far more intense and complex way than it is on any solid world. Inside a star, gravity is not confined to a surface. It acts throughout the entire volume, shaping structure, motion, and long-term stability from the center outward. A star begins as a cloud of gas and dust drawn together by gravity. As material accumulates, gravitational attraction strengthens, pulling more matter inward. Over time, this inward pull becomes strong enough to compress the central regions of the forming star. Temperatures rise, densities increase, and nuclear fusion begins. At this point, gravity does not disappear. Instead, it becomes part of a delicate balance. Inside an active star, gravity constantly pulls matter inward toward the core. At the same time, energy released by nuclear fusion produces heat and pressure that push outward. The state in which these opposing effects balance is known as hydrostatic equilibrium. It is this balance that allows stars to shine steadily for millions or billions of years without collapsing or tearing themselves apart. Hydrostatic equilibrium is not static or fragile. It is a dynamic balance maintained moment by moment. If the core contracts slightly, temperatures rise, fusion rates increase, and outward pressure strengthens, restoring balance. If the core expands, temperatures fall, fusion slows, and gravity gains the upper hand again. This self-regulating process keeps stars stable across immense timescales. The strength of gravity inside a star depends strongly on stellar mass. More massive stars have stronger gravity throughout their interiors. This increased gravitational pressure raises core temperatures and accelerates nuclear fusion. As a result, massive stars burn through their fuel much faster than smaller ones. They shine brighter, live shorter lives, and experience more extreme internal conditions. In smaller stars, including the Sun, gravity is strong enough to sustain fusion but not so strong as to drive it rapidly. The Sun's mass produces core temperatures of roughly 15 million degrees Celsius, sufficient to fuse hydrogen into helium at a steady pace. This balance allows the Sun to remain stable for billions of years, providing a long window for life to develop on nearby planets. Gravity inside stars also determines how energy moves outward. In some regions, energy travels through radiation, with photons scattering repeatedly as they move toward the surface. In other regions, energy is transported by convection, with hot plasma rising and cooler material sinking. The structure of these layers is governed by the interplay between gravity, pressure, and temperature. Solar physics has provided detailed insight into this internal structure. Helioseismology, the study of oscillations on the Sun's surface, allows scientists to probe its interior indirectly. By measuring how waves travel through the Sun, researchers infer density, temperature, and motion deep beneath the visible surface. These measurements confirm theoretical models of how gravity shapes the Sun from within. Data from missions such as the Solar and Heliospheric Observatory and the Solar Dynamics Observatory have refined this picture further. Observations of solar vibrations, magnetic fields, and energy output all point to gravity as the organizing framework that holds the star together. Without gravity, nuclear fusion would disperse the star's material into space. Without fusion, gravity would cause the star to collapse. The balance between gravity and fusion is not permanent. As stars age and fuel supplies change, gravity gradually gains influence. When hydrogen in the core is depleted, fusion slows. Outward pressure weakens. Gravity responds by compressing the core further, raising temperatures until new fusion processes begin, if possible. This sequence drives stellar evolution and determines a star's ultimate fate. In very massive stars, gravity eventually overwhelms all opposing forces. When fusion can no longer provide sufficient pressure, the core collapses rapidly, leading to dramatic events such as supernova explosions. Even in these violent moments, gravity remains central, guiding collapse, rebound, and the formation of dense remnants. What is striking is that gravity inside stars does not merely pull material inward. It sets the conditions for energy production, regulates stability, and determines lifespan. It acts as an internal architect, shaping the star from the inside out rather than operating only at a surface boundary. This view expands gravity's role beyond what is experienced on solid worlds. On planets, gravity defines weight and structure. Inside stars, gravity governs balance, transformation, and long-term change. The same interaction that holds feet to the ground also sustains the steady light of stars across the galaxy. Understanding gravity inside stars highlights its versatility. It adapts to different forms of matter, from solid rock to hot plasma, while obeying the same underlying principles. This continuity is what allows gravity to operate across such a wide range of environments without contradiction. By recognizing gravity as an internal organizing force, the behavior of stars becomes less mysterious. Their stability, brightness, and evolution all follow naturally from the balance between inward pull and outward energy. Gravity does not simply act on stars. It defines what it means for a star to exist at all. Not all objects in the solar system are large enough for gravity to dominate their behavior in obvious ways. Beyond planets and large moons lies a population of small bodies where gravity operates at its weakest practical extreme. Asteroids, comets, and tiny moons occupy a regime where gravity is present but barely assertive, shaping environments that feel almost untethered. On these bodies, gravity is often described as microgravity. This does not mean gravity is absent. It means the gravitational acceleration at the surface is extremely small compared to that of Earth. On some asteroids, surface gravity can be tens of thousands of times weaker than Earth's. A gentle push could send an object drifting away at walking speed, never to return. This weak gravity arises from limited mass combined with small size. Many asteroids are only a few kilometers across, and some are far smaller. Even though they may be composed of rock or metal, there is simply not enough mass concentrated in one place to generate a strong gravitational field. The result is a world where weight is barely felt. Comets present a similar case, though with different composition. Often described as icy rubble piles, comets are mixtures of frozen gases, dust, and rock loosely held together. Their gravity is so weak that material can escape easily when heated by the sun. Jets of gas and dust stream outward, forming tails that stretch millions of kilometers through space. Gravity attempts to hold the comet together, but thermal forces frequently overpower it. Small moons orbiting planets also illustrate this regime. Some moons of Mars and the outer planets are irregularly shaped and lightly bound. Their gravity is strong enough to keep them intact under calm conditions, but not strong enough to reshape them into spheres. Many retain elongated or lumpy forms, reflecting their weak internal gravitational pull. In these environments, geology behaves very differently. On Earth, gravity drives landslides, erosion, and the settling of material into layers. On small bodies, loose material does not flow easily downhill because downhill is poorly defined. A slight disturbance can loft dust into space rather than causing it to settle. Surface features reflect this. Craters remain sharp and unchanged for long periods because erosion is minimal. Debris accumulates where it lands, not where gravity would normally draw it. Even walking on such a surface, if it were possible, would resemble slow-motion bouncing rather than stepping. Space missions have provided direct insight into these conditions. The Japanese Hayabusa mission visited the asteroid Itokawa and revealed a surface covered in loose gravel rather than solid bedrock. The asteroid appeared to be a rubble pile, a collection of fragments gently held together by gravity alone. This confirmed long-standing theories that many asteroids are not monolithic rocks, but loosely assembled structures. The European Space Agency's Rosetta mission offered a similar window into cometary gravity. By orbiting and eventually deploying a lander onto Comet 67P Churyumov-Gerasimenko, Rosetta demonstrated just how weak gravity can be. The lander bounced upon contact because gravity was insufficient to hold it firmly in place. Anchoring systems struggled because even small mechanical forces overwhelmed the comet's pull. These missions revealed an important truth. Weak gravity allows objects to exist in states that would be impossible on larger worlds. Loose material can remain exposed. Cavities can persist without collapsing. Internal structure can be fragile yet stable over long periods because external disturbances are rare. Gravity in these settings also reshapes internal structure. Without strong compression, material inside small bodies remains porous. Voids persist. Density varies irregularly. These characteristics influence how such objects respond to impacts, heating, and tidal forces from nearby planets. Even so, gravity still matters. It determines whether material escapes or returns. It governs orbital motion and long-term stability. It defines the boundary between what remains part of the body and what drifts away into space. The difference is one of degree, not of presence. Comparing these environments to planets highlights how scale transforms gravity's role. On planets, gravity dominates structure and motion. On small bodies, gravity is one influence among many, often competing with thermal forces, impacts, and rotational effects. This contrast reveals the lower limit of gravitational strength in the universe, as it is commonly experienced. There are environments where gravity is just strong enough to assemble material, but not strong enough to impose order. These worlds sit delicately balanced between cohesion and dispersal. Understanding gravity around small bodies completes the picture of variation within a single system. From crushing gravity inside stars to the barely perceptible pull of an asteroid, the same fundamental interaction operates across an enormous range of strengths. Gravity does not disappear as objects grow smaller. It simply becomes quieter, subtler, and easier to overlook. Orbit often feels unintuitive because it seems to contradict everyday experience. Objects that are dropped fall straight down. Objects that are thrown forward eventually land. From the surface of Earth, motion and falling appear to be separate things. In space, they are deeply connected. An orbit is not an object escaping gravity. It is an object falling continuously while never reaching the ground. This idea was described clearly by Isaac Newton through a simple thought experiment known as Newton's cannon. Imagine a cannon placed on a very high mountain, far above the atmosphere. A cannonball fired gently would fall to the ground not far from the mountain's base. Fired with more force, it would travel farther before landing. Increase the speed enough, and the cannonball would curve around the planet, falling toward Earth, but missing it entirely. In that case, the cannonball would be in orbit. The key insight is that gravity pulls the cannonball downward at all times. What changes is the forward motion. When forward speed is high enough, the surface of the planet curves away beneath the falling object. The object is always falling, but the ground is always falling away at the same rate. The result is a stable path around the planet. This reframes orbit as a balance between motion and gravity rather than a state of escape. Objects in orbit are not beyond Earth's gravitational reach. In low Earth orbit, gravity is only slightly weaker than it is at the surface. The International Space Station experiences nearly 90% of Earth's surface gravity, yet everything aboard appears weightless. This apparent contradiction leads to one of the most common misconceptions in space science, the idea of zero gravity. Astronauts are often described as floating because gravity is absent. In reality, gravity is very much present. What is absent is a supporting force. Weight is not the same as gravity. Weight arises when gravity is resisted by a surface. Standing on Earth, the ground pushes upward in response to gravity pulling downward. This interaction creates the sensation of weight. In orbit, there is no surface providing that upward push. Astronauts, spacecraft, and everything inside them are all falling together under gravity. Because everything is falling at the same rate, there is no relative motion between objects inside the spacecraft. Tools float, bodies drift, liquids form spheres. This condition is more accurately described as microgravity, or free fall, rather than zero gravity. The sensation of weightlessness comes from constant falling, not from the absence of gravity. This concept aligns closely with the modern understanding of gravity as geometry. In curved spacetime, objects move along natural paths unless acted upon by other forces. An orbiting spacecraft follows such a path around Earth. Gravity guides motion rather than pulling objects inward like a rope. Seen this way, orbit is not an active struggle against gravity. It is a passive response to it. The spacecraft does not need to continuously thrust to stay in orbit. Once placed on the correct path, it follows that path naturally, shaped by Earth's mass and the curvature of space-time around it. This perspective also explains why orbits can exist around many different objects. Moons orbit planets, planets orbit stars, stars orbit the centers of galaxies. In each case, gravity provides the curvature, and motion carries objects along stable paths through that curved environment. Distance plays a role in shaping these paths. Closer orbits require higher speeds to avoid falling inward. Farther orbits require less speed because gravity is weaker. These relationships can be calculated precisely, but the underlying idea remains simple. Orbital motion is continuous falling guided by gravity. The idea can feel counterintuitive because falling is usually associated with collision. On Earth, falling objects hit the ground quickly. In orbit, the scale is different. The curvature of the planet becomes part of the motion. Falling continues endlessly without impact as long as the path remains clear. Understanding orbit this way dissolves many common confusions. Satellites do not hover above Earth. They are not held up by outward forces. They are moving forward fast enough that their fall becomes a curve rather than a drop. This framing also helps explain why orbits can decay. Atmospheric drag, even very thin, slows objects slightly. Forward speed decreases. The balance shifts. The path curves more steeply inward, and the object eventually re-enters the atmosphere. Gravity remains constant throughout. What changes is motion. By viewing orbit as continuous falling, gravity becomes less mysterious and more subtle. It does not act as a simple downward pull that must be overcome. It shapes the pathways that objects naturally follow through space. Motion and gravity work together, producing stability without stillness. This understanding deepens the idea that gravity guides rather than restrains. It allows objects to move freely while remaining bound. What looks like suspension is actually perpetual descent, carefully matched to the curve of the world below. Empty space is often imagined as a place where gravity fades away, where distance dilutes influence until nothing meaningful remains. When stars disappear and galaxies recede into darkness, it can feel intuitive to assume that gravity must weaken to the point of absence. In reality, gravity does not vanish in empty space. It becomes quieter, more diffuse, and harder to notice, but it never fully leaves. What changes in regions far from stars and galaxies is not whether gravity exists, but how it is expressed. In dense environments, gravity is obvious. Objects fall, orbits tighten, and motion curves clearly. In sparse environments, gravity still operates, but its effects unfold slowly, stretched across immense distances and long spans of time. The absence of nearby matter does not remove gravity. It only reduces its immediate intensity. Gravity does not require visible objects nearby to function. Any object with mass contributes to the structure of space-time, and each contribution extends outward indefinitely. The influence weakens with distance, but it does not stop. A star affects space-time far beyond the reach of its light. A galaxy shapes motion well outside its luminous edge. Even when no obvious source is close, gravity reflects the combined influence of many distant masses. Interstellar space offers a useful example. Between stars, distances are vast, yet gravity remains active. Stars within a galaxy do not drift independently through emptiness. They orbit a shared center, guided by the collective gravitational field of billions of stars, clouds of gas, and unseen matter. At any point between stars, gravity is the result of overlapping influences. No single object dominates, but together they define how motion unfolds. Intergalactic space extends this idea further. Between galaxies, matter is extraordinarily sparse. Light can travel for millions of years without encountering a star. Even so, galaxies continue to move in structured ways. They drift toward clusters, trace long filaments, and avoid enormous regions known as cosmic voids. These patterns exist not because gravity is absent in empty space, but because gravity has already acted, pulling matter into denser regions and leaving behind quieter expanses. The idea of overlapping gravitational influence is central to understanding this behavior. Gravity does not come from one object acting alone. At every location in the universe, the gravitational environment reflects the sum of all relevant masses near and far. Nearby objects contribute strongly. Distant objects contribute weakly. Together, they form a continuous gravitational background rather than isolated zones of influence. This is why gravity cannot be escaped simply by travelling far from objects. Distance changes the balance of influences, but it does not remove them entirely. Even in the emptiest known regions of the universe, gravity still shapes how matter moves and how structures evolve. Large-scale cosmic surveys have revealed this structure with remarkable clarity. Observations from projects such as the Sloan Digital Sky Survey and the Dark Energy Survey map the distribution of galaxies across enormous volumes of space. These maps show that galaxies are not scattered randomly. They form a vast network often called the cosmic web, made up of filaments, clusters, and immense voids. This structure emerged over billions of years through gravitational interaction alone. Cosmic voids are sometimes mistaken for places where gravity does not exist. In fact, they are evidence of gravity at work. These regions are empty because gravity has pulled matter away from them. Small differences in density in the early universe were amplified over time as gravity drew material into denser regions. The voids themselves continue to evolve, expanding and reshaping under the same gravitational influence. From the perspective of general relativity, empty space is never truly empty. Space-time exists everywhere, regardless of how much matter is present. Its geometry reflects the total mass and energy of the universe, including contributions from objects far beyond the local environment. In regions with little nearby matter, space-time is closer to flat, but it is never completely free of curvature. This helps explain why motion through deep space remains predictable. Spacecraft traveling between planets are not drifting aimlessly. Their paths are guided by the combined gravity of the Sun, planets, and more distant bodies. Even when a spacecraft appears to be moving through emptiness, its trajectory reflects a carefully calculated gravitational landscape shaped by many sources. Gravity in empty space also plays a role in the long-term evolution of the universe. Over short timescales, weak gravitational influences seem insignificant. Over billions of years they accumulate. Small accelerations, barely noticeable in isolation, reshape structure across cosmic history. Galaxies drift together. Groups form clusters. Clusters assemble into even larger systems. None of this requires strong local gravity. It emerges from persistent, overlapping influence. Understanding gravity in empty space removes the idea that gravity must be tied to visible matter nearby. It is not something that switches on near planets and turns off elsewhere. It is a continuous feature of the universe, woven into space-time itself. What changes from place to place is not the presence of gravity, but the strength and balance of its effects. This perspective also explains why gravity feels local despite being universal. In any given place, nearby masses dominate experience. Distant masses contribute quietly, setting background conditions rather than obvious motion. Gravity is always present, but its expression depends on scale. Empty space, then, is not free of gravity. It is where gravity becomes subtle rather than dramatic. Without nearby objects to mark its presence, its influence unfolds slowly, shaping motion and structure over immense distances. What appears empty is still structured. What seems inactive is still governed. Gravity does not need crowded regions to exist. It only needs mass somewhere in the universe to leave its imprint everywhere. Gravity does more than guide motion and shape structure. It also influences time itself. This idea can feel strange because time is usually experienced as something steady and universal, ticking forward at the same rate everywhere. In everyday life, seconds feel identical whether they pass in a city, on a mountain, or deep underground. Yet according to modern physics, time does not flow at a single universal pace. It changes with gravity. This effect is known as gravitational time dilation, a prediction of Albert Einstein's theory of general relativity. The core idea is that gravity and time are linked through the geometry of spacetime. Where gravity is stronger, spacetime is more curved. That curvature affects not only how objects move, but how time passes. In regions of stronger gravity, time runs more slowly. In regions of weaker gravity, time runs more quickly. The difference is not dramatic in most everyday situations, but it is real, measurable, and unavoidable. Two identical clocks placed at different gravitational strengths will not remain synchronized. One will tick slightly faster than the other. Near Earth's surface, gravity is relatively strong compared to higher altitudes. A clock on the ground ticks a little more slowly than a clock aboard a satellite in orbit. The satellite is farther from Earth's mass, experiencing weaker gravity, and so its clock runs faster. The difference is tiny, amounting to fractions of a second over long periods, but it accumulates steadily. This is not a theoretical curiosity. It has been measured directly. Experiments using atomic clocks, which can keep time with extraordinary precision, have demonstrated gravitational time dilation even across small height differences. A clock placed a few meters higher than another will tick slightly faster. The effect is subtle, but modern instruments are sensitive enough to detect it. One of the most important practical demonstrations of gravitational time dilation comes from the Global Positioning System. GPS satellites orbit Earth at high altitude and high speed. Their onboard atomic clocks are affected by two time dilation effects. Because the satellites move quickly, special relativity predicts their clocks should tick more slowly. Because they are farther from Earth and experience weaker gravity, general relativity predicts their clock should tick more quickly. Both effects must be accounted for. The gravitational effect is stronger than the velocity effect, so overall, GPS satellite clocks tick faster than clocks on Earth's surface. Engineers correct for this difference deliberately. If these corrections were not applied, GPS positioning errors would grow rapidly, leading to location errors of kilometers within a single day. The system works precisely because gravitational time dilation is real and well understood. Despite this, gravitational time dilation goes unnoticed in daily life. The reason is scale. The differences in gravitational strength between common locations are small, and the resulting time differences accumulate very slowly. Over a human lifetime, the difference between time experienced at sea level and at the top of a mountain is measurable but modest. No sensation accompanies it. There is no feeling of time slowing or speeding up. This absence of sensation does not mean time behaves uniformly. It means human perception is not equipped to notice such fine differences. Just as gravity feels constant despite small variations, time feels steady because the changes are too subtle to register directly. The effect becomes more dramatic near very massive objects. Close to a neutron star or a black hole, gravitational time dilation becomes extreme. Time near the surface of a neutron star runs significantly more slowly than time far away. Near the edge of a black hole, known as the event horizon, time dilation grows so strong that, from the perspective of a distant observer, time appears to slow almost to a stop. These extreme cases are not part of everyday experience, but they follow from the same principles that govern time near Earth. The difference is one of degree, not kind. Gravity influences time everywhere. Strong gravity makes the effect obvious. Weak gravity makes it subtle. Gravitational time dilation also reinforces the idea that time is not separate from space. Together, They form spacetime, a unified structure shaped by mass and energy. Where spacetime curves more strongly, both motion and time behave differently. This unity explains why gravity affects clocks without any additional mechanism. Time is part of the same structure that gravity shapes. It is important to clarify that this does not mean time flows incorrectly or unpredictably. Time behaves exactly as described by the underlying geometry of spacetime. Clocks do not malfunction in strong gravity. They tick normally according to their local conditions. It is only when clocks in different gravitational environments are compared that differences appear. Each clock measures its own proper time, the time experienced locally. There is no universal master clock ticking in the background of the universe. Time is local, just as gravity is local. What feels simultaneous in one place may not align perfectly with what feels simultaneous elsewhere when gravity differs. This challenges intuitive ideas about time being absolute. In Newtonian physics, time was treated as universal, flowing at the same rate everywhere regardless of conditions. General relativity replaces this with a more flexible picture, where time adapts to the shape of space-time. Gravity reshapes that shape and time follows. Even so, this does not make time chaotic or subjective. The rules governing gravitational time dilation are precise and consistent. They allow predictions that match observation with extraordinary accuracy. Time changes with gravity in predictable ways that can be measured, calculated, and corrected for. The influence of gravity on time also has implications for long-term cosmic history. Over billions of years, regions of the universe with different gravitational environments accumulate different amounts of elapsed time. Clocks near massive clusters tick slightly slower than clocks in emptier regions. The differences are small, but they are real, woven into the universe's timeline. Understanding gravitational time dilation expands the role of gravity beyond structure and motion. Gravity does not merely guide objects along paths or hold systems together. It shapes the rate at which events unfold. It influences how long processes take, how signals propagate, and how histories align. This connection between gravity and time deepens the idea that gravity is not just another force among many. It is a fundamental feature of space-time itself. Where gravity changes, time responds. Where mass accumulates, the pace of time subtly shifts. For everyday life, this remains an invisible effect. Clocks on a table tick together. Time feels steady. But beneath that calm surface, time is quietly responsive to gravity, stretching and compressing in ways that only precise measurement reveals. Recognizing this does not make time feel unstable. Instead, it places time within a broader context. Time is not detached from the universe's structure. It is shaped by it. Gravity reaches beyond falling objects and orbiting worlds, extending into the rhythm of moments themselves. Gravity reaches its most extreme known expressions around neutron stars and black holes. These objects represent environments where mass is packed so densely that space-time itself is pushed to its limits. The same principles that govern falling apples and orbiting satellites still apply, but their effects are intensified to degrees that strain intuition and demand careful explanation. A neutron star forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. During this collapse, the core is compressed so intensely that protons and electrons merge to form neutrons. The result is an object with a mass greater than that of the Sun squeezed into a sphere only a few tens of kilometers across. This concentration of mass creates an extraordinarily strong gravitational field. Near the surface of a neutron star, gravity is billions of times stronger than it is on Earth. an object dropped from even a small height would strike the surface at a significant fraction of the speed of light. Mountains, if they can be called that, rise only centimeters high before collapsing under their own weight. Matter behaves in unfamiliar ways because gravity dominates every aspect of structure and motion. Escape velocity provides a useful way to describe this intensity. Escape velocity is the speed an object must reach to break free from a gravitational field without further propulsion. On Earth, escape velocity is about 11 kilometers per second. On a neutron star, escape velocity approaches a large fraction of the speed of light. This means that once matter is near the surface, leaving becomes extremely difficult. The immense gravity of neutron stars also produces strong tidal forces. Tidal forces arise because gravity pulls more strongly on the nearer parts of an object than on the farther parts. Near Earth, tidal forces are gentle, responsible for ocean tides. Near a neutron star, these forces are extreme. Objects can be stretched, compressed, or torn apart by the difference in gravitational pull across their length. Spacetime curvature near neutron stars is intense. Paths that would be straight elsewhere become sharply bent. Light itself is affected, curving around the star and altering how it appears to distant observers. Time dilation becomes significant. Clocks near the surface tick much more slowly than clocks far away. These effects are not theoretical curiosities. They are predicted precisely by general relativity and supported by observation. Black holes represent an even more extreme outcome of gravitational collapse. When a collapsing core exceeds a certain mass, no known force can halt the inward pull of gravity. The result is a region of space-time from which nothing can escape once a critical boundary is crossed. This boundary is known as the event horizon. The event horizon is not a physical surface, it is a boundary in space-time. Outside it, escape is possible in principle. Inside it, all possible paths lead inward. The escape velocity at the event horizon equals the speed of light. Since nothing can travel faster than light, escape becomes impossible. It is important to clarify what this means. Gravity at the event horizon is not infinite. Objects crossing it do not encounter an abrupt wall or sudden crushing force, especially for large black holes. What changes is the structure of space-time itself. Directions that once led outward now point inward. Falling inward becomes as inevitable as moving forward in time. Closer to the center of a black hole, space-time curvature grows stronger. Tidal forces increase dramatically. In some cases, these forces would stretch objects into long, thin shapes, in a process sometimes called spaghettification. This effect arises because the gravitational pull at the near end of an object is much stronger than at the far end. Escape velocity and spacetime curvature are closely linked in these environments. As gravity intensifies, spacetime curves more sharply. Motion becomes increasingly constrained. The idea of gravity as a pulling force gives way almost entirely to gravity as geometry. Objects follow paths dictated by spacetime itself. For a long time, neutron stars and black holes were studied only indirectly. Their gravity revealed their presence through effects on nearby matter. Stars orbiting invisible companions, gas heating and emitting radiation as it spiraled inward, precise timing variations in pulsars, which are rapidly rotating neutron stars emitting regular beams of radiation. In recent years, direct observational evidence has transformed understanding. The Laser Interferometer, gravitational wave observatory known as LIGO, detected gravitational waves produced by the merging of black holes and neutron stars. These waves are ripples in spacetime itself, generated by accelerating masses in extreme gravitational fields. Their detection confirmed key predictions of general relativity and provided new insight into gravity at its strongest. Another breakthrough came from the Event Horizon Telescope, a global network of radio observatories that produce the first images of black hole shadows. These images show light bent and captured by intense gravity near the event horizon. They do not show the black hole itself, but the effect of its gravity on surrounding matter and radiation. These observations anchor extreme gravity firmly in reality. Neutron stars and black holes are not theoretical oddities. They are common outcomes of stellar evolution, scattered throughout galaxies, influencing their surroundings through gravity alone. Despite their intensity, these environments do not require new physical laws. The same equations that describe gravity near Earth describe gravity near a black hole. The difference lies in scale. When mass is concentrated enough, familiar effects become dramatic. This contrast highlights gravity's full range. Earlier environments showed gravity as gentle, barely noticeable, or quietly shaping motion over time. Near extreme objects, gravity becomes dominant, overwhelming other influences and revealing aspects of spacetime that remain hidden elsewhere. It is also worth noting that even in these extreme settings, gravity behaves predictably. Paths can be calculated, time dilation can be measured, tidal forces follow precise relationships. There is no chaos in the laws themselves, only intensity in their consequences. Understanding gravity near neutron stars and black holes completes the spectrum. From barely perceptible pull around small bodies to crushing curvature near collapsed stars, gravity reveals itself as a single interaction expressed across many scales. These extremes do not invalidate the calm familiarity of gravity elsewhere. They contextualize it. The quiet downward pull felt on Earth is one expression of the same phenomenon that bends light, slows time, and traps matter near the most extreme objects in the universe. Gravity does not change its nature in these places, it reveals it. Between stars, gravity operates on scales that stretch far beyond individual systems. A single star is shaped by its own mass and internal balance, but no star exists in isolation. Each one moves within a broader gravitational environment, influenced by countless others over immense distances and long spans of time. Within a galaxy, stars orbit a shared center of mass. This center is not usually marked by a single object, but by the combined mass of stars, gas, dust, and unseen matter distributed throughout the galaxy. Each star follows a path determined by this collective gravitational field, tracing wide arcs that can take hundreds of millions of years to complete. These stellar orbits are not rigid or perfectly circular. They're shaped by the uneven distribution of mass within the galaxy. Regions with more mass exert stronger influence, subtly altering stellar paths. Over time, stars drift inward or outward, tilt their orbital planes, or change speeds slightly, all guided by gravity acting patiently across deep time. Star clusters provide a more intimate setting for gravitational interaction. In these dense groups, stars are born together from the same cloud of gas. At first, they are tightly packed, their mutual gravity binding them into a shared system. Each star feels the pull of many neighbors at once, creating a constantly shifting pattern of influence. In open clusters, which contain hundreds or thousands of stars, gravity is strong enough to hold the group together for millions of years. Over time, however, interactions between stars gradually alter their motions. Close encounters exchange energy. Some stars are nudged into wider orbits, others gain enough speed to escape the cluster entirely. Gravity both binds and slowly dissolves these systems. Globular clusters represent a more extreme case. These ancient structures contain hundreds of thousands, sometimes millions, of stars packed into relatively small volumes of space. Gravity dominates their internal dynamics. Stellar motions are fast and complex, interactions are frequent. Yet despite this activity, globular clusters can remain intact for billions of years, held together by the combined gravitational pull of their members. Within clusters, gravity governs not just motion, but long-term evolution. Massive stars tend to sink toward the center through a process known as mass segregation. Lighter stars drift outward. Over time, the cluster develops a layered structure shaped entirely by gravitational interaction. This quiet sorting unfolds slowly, unnoticed on human timescales, but unmistakable across cosmic history. Between clusters and across galactic disks, gravity continues its work. Stars do not travel in straight lines through space. They follow curved paths shaped by the galaxy's overall mass distribution. Spiral galaxies, for example, maintain their structure through gravitational balance. Stars move faster closer to the center and more slowly farther out, yet the galaxy remains coherent rather than flying apart. Galactic dynamics research seeks to understand these motions in detail. By measuring stellar velocities and positions, astronomers infer the underlying gravitational field. Observations of star motion reveal discrepancies between visible mass and gravitational effects, pointing to the presence of dark matter. Gravity, once again, exposes what cannot be seen directly. Over millions of years, these gravitational interactions reshape stellar neighborhoods. Stars migrate from their birthplaces, clusters disperse, new groupings form. The galaxy remains dynamic, constantly rearranging itself under gravity's guidance. Nothing is fixed. Stability exists only in motion. Gravity between stars also influences the likelihood of encounters. In dense regions, stars can pass close enough to disturb planetary systems, altering orbits or ejecting planets entirely. In sparser regions, stars pass one another silently, separated by vast distances. The local gravitational environment determines how often such interactions occur. Despite the complexity, these motions are not random. They follow patterns that can be modelled and predicted. Gravitational interactions obey consistent rules, even when many bodies are involved. Over time, these rules produce large-scale order from countless individual motions. One striking feature of stellar gravity is how slow its effect can be. A star may take hundreds of millions of years to complete a single orbit around the galactic center. Changes that would seem imperceptible over centuries accumulate into significant rearrangements over cosmic timescales. Gravity works patiently, shaping systems without urgency. This long view helps explain why galaxies appear stable despite constant motion. Stars move, clusters evolve, and matter flows, yet the overall structure persists. Gravity provides cohesion without rigidity. It allows flexibility while maintaining form. Understanding gravity between stars marks a transition from thinking about isolated objects to thinking about collective systems. Gravity is no longer just something that binds a planet to a star or a star to itself. It becomes the organizing principle for entire populations of stars moving together through space. This perspective also prepares the way for understanding gravity on even larger scales. The same principles that govern stars within a galaxy apply to galaxies within clusters and clusters within the cosmic web. The scale changes, but the underlying interaction remains the same. Between stars, gravity is subtle rather than dramatic. It does not announce itself through sudden motion or visible collapse. Instead, it reveals itself through patterns, regularities, and slow evolution. It connects individual stars into a shared story, one written over millions and billions of years. By following how stars move together rather than alone, gravity emerges not as a local force, but as a communal influence. It binds systems, shapes histories, and carries structure forward through time. What appears calm and static from a distance is, in reality, a quiet choreography guided by gravity at work between the stars. Galaxies appear serene when viewed from afar. Vast spirals of stars rotate slowly against the dark background of space, their shapes remaining stable across millions of years. This calm appearance hides an ongoing gravitational process that governs how galaxies form, move, and persist. At this scale, gravity is no longer just guiding individual stars, it is shaping entire structures. In spiral galaxies, gravity plays a central role in maintaining the familiar disk and arm pattern. Stars orbit a shared galactic center, but they do not all move at the same speed. Those closer to the center complete their orbits more quickly, while those farther out take longer. This differential motion stretches and organizes material into spiral patterns rather than tearing the galaxy apart. Spiral arms are not fixed structures made of the same stars forever. Instead, they are regions where stars, gas, and dust are temporarily concentrated. Gravity causes material to bunch up as it moves through the galactic disk, much like traffic slowing along a busy roadway. As gas clouds compress, star formation is triggered, lighting up the arms and making them visible across vast distances. This process depends critically on gravity acting across the entire galaxy. The combined mass of stars, gas, and other material creates a gravitational field that holds the disk together and allows spiral patterns to persist. Without sufficient gravitational binding, the rotating disk would disperse over time. When astronomers began measuring how stars move within galaxies, they encountered a puzzling result. According to classical expectations, stars farther from the galactic center should orbit more slowly, much like planets farther from the Sun move at lower speeds. The visible mass of stars and gas suggested a certain decline in orbital speed with distance. Instead, observations showed that stars far from the center were moving much faster than expected. Their speeds remained roughly constant across large distances. This pattern, known as a flat rotation curve, implied that there was more gravitational influence present than could be explained by visible matter alone. This discrepancy was studied in detail by astronomer Vera Rubin in the 1970s. By carefully measuring the rotation curves of spiral galaxies, Rubin demonstrated that the visible stars and gas could not account for the observed motion. Galaxies appeared to contain far more mass than could be seen. The most widely accepted explanation for this hidden gravitational influence is dark matter. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred entirely through gravity. Galaxies appear to be embedded in large halos of dark matter that extend far beyond their visible edges. These dark matter halos provide the additional gravitational pull needed to explain flat rotation curves. Stars orbiting in the outer regions of galaxies move quickly because they are responding to the gravity of both visible matter and this unseen mass. Without dark matter, many galaxies would not remain stable over cosmic time. Gravity thus becomes a tool for discovery. It reveals components of the universe that cannot be detected directly. By studying how galaxies rotate and how their structures persist, astronomers map the distribution of mass that would otherwise remain hidden. This realization reshaped understanding of galaxies. They are not simply collections of stars floating in space. They are gravitational systems dominated by material that cannot be seen. Visible stars trace the deeper structure imposed by dark matter rather than defining it. Gravity also explains why galaxies come in different forms. Spiral galaxies maintain flattened disks because gravity and angular momentum balance in a particular way. Elliptical galaxies, by contrast, have more random stellar motions, often resulting from mergers that redistribute energy through gravity. Irregular galaxies show distorted shapes where gravitational interactions have disrupted orderly motion. Interactions between galaxies further highlight gravity's role. When galaxies pass close to one another, their mutual gravity can stretch stars into long tidal streams, distort spiral arms, and even trigger bursts of star formation. Over time, repeated interactions can lead to mergers, forming larger galaxies with new structures. These processes unfold over hundreds of millions to billions of years. Gravity acts slowly but persistently, reshaping galaxies without urgency. The present appearance of a galaxy reflects a long history of gravitational influence rather than a static configuration. Galactic gravity also affects gas within galaxies. Gas clouds respond to gravitational potential wells, flowing inward toward denser regions. This inflow feeds star formation and, in some cases, central supermassive black holes. Again, gravity acts as an organizer, guiding material toward regions where transformation occurs. Supermassive black holes at galactic centers contribute to this picture, but they do not dominate galactic gravity beyond their immediate surroundings. The motion of stars across most of a galaxy is governed primarily by the combined mass of stars and dark matter, not by the central black hole alone. This underscores how gravity operates collectively rather than locally at this scale. The study of galactic dynamics continues to refine this understanding. Large observational surveys and detailed simulations allow astronomers to compare predicted motion with real data. When discrepancies appear, they point not to failures of gravity itself, but to missing components in the mass budget. In this way, gravity becomes a guide rather than a mystery. It consistently reveals when something is absent from the visible picture. Dark matter was not proposed because it was observed directly, but because gravity demanded its existence to explain what galaxies were doing. This makes gravity in galaxies especially revealing. It shows that gravity does not merely respond to what can be seen. It responds to everything that exists, whether visible or not. Motion becomes evidence. Structure becomes testimony. By expanding gravity's scope beyond visible matter, galaxies demonstrate how much of the universe is known indirectly. Stars outline shapes, but gravity defines them. Light shows surfaces, but gravity reveals depth. At this scale, gravity is no longer just a force that binds objects. It is a diagnostic tool, exposing the universe's hidden architecture. The graceful rotation of galaxies is not just a visual spectacle. It is a record of mass, motion, and invisible structure written in gravity's language. Through galaxies, gravity teaches that absence of light does not mean absence of influence. What cannot be seen can still shape everything around it. Gravity makes that influence measurable, consistent, and unavoidable. The calm spirals scattered across the universe are held together not only by what shines, but by what remains unseen. Gravity bridges that gap, turning motion into evidence and revealing that much of the universe's substance lies beyond the reach of light, but never beyond the reach of gravity. Between galaxies, gravity operates on scales so large that motion unfolds over hundreds of millions to billions of years. Individual galaxies may seem isolated when viewed alone, but in reality they are part of vast gravitational systems that bind them together into clusters, groups, and even larger structures. At this scale, gravity reveals itself not through sudden motion, but through slow organization across immense distances. Galaxy clusters are the most massive gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies, along with enormous amounts of hot gas and dark matter. The galaxies within a cluster are not fixed in place. They move through the cluster's gravitational potential, orbiting a shared center of mass shaped by everything present, visible and invisible alike. These motions are slow but persistent. A single orbit through a galaxy cluster can take billions of years. Over such timescales, gravity gently guides galaxies along curved paths, drawing them inward, redirecting them, or allowing them to pass by one another without collision. The cluster remains bound because the total gravitational pull is strong enough to overcome the tendency of galaxies to drift apart. The binding force in galaxy clusters is far greater than what visible matter alone can provide. Stars and glowing gas account for only a fraction of the mass required to hold clusters together. Most of the gravitational influence comes from dark matter, distributed throughout the cluster in a vast extended halo. Once again, gravity exposes what cannot be seen directly. One of the clearest pieces of evidence for this hidden mass comes from gravitational lensing. According to general relativity, mass curves spacetime, and that curvature affects the path of light. When light from a distant galaxy passes near a massive object or cluster, its path bends. The result can be distorted images, stretched arcs, or even multiple copies of the same background galaxy. Gravitational lensing allows astronomers to map mass directly, regardless of whether it emits light. By studying how background galaxies are distorted, scientists reconstruct the distribution of mass within clusters. These reconstructions consistently show far more mass than is visible. The lensing signal traces dark matter with remarkable clarity. Both the European Space Agency and NASA have played major roles in these observations. Space telescopes such as the Hubble Space Telescope and the James Webb Space Telescope have captured detailed lensing images of massive galaxy clusters. These images reveal intricate arcs of light shaped by gravity acting across intergalactic space. X-ray observatories, including ESA's XMM Newton and NASA's Chandra X-ray Observatory, add another layer of evidence. They detect hot gas trapped within clusters, glowing due to extreme temperatures. This gas contributes to the cluster's mass, but even when accounted for, it cannot explain the full gravitational effect. Dark matter remains essential. Gravity between galaxies does more than hold clusters together, it also governs how clusters evolve. Galaxies falling into a cluster accelerate as they approach denser regions. Their shapes can be distorted by tidal forces. Gas can be stripped away as galaxies move through the hot intracluster medium. These processes are slow but transformative, reshaping galaxies over time. Clusters themselves are not isolated. They are connected to other clusters through long filaments of galaxies and dark matter. These filaments form part of the cosmic web, the largest known structure in the universe. Gravity drives matter along these filaments, feeding clusters and superclusters over billions of years. At the intersections of filaments, gravity becomes especially influential. Matter accumulates. Clusters grow. The universe's large-scale structure emerges from the gradual amplification of tiny density differences present shortly after the Big Bang. Gravity turns those small variations into vast networks spanning hundreds of millions of light-years. What is striking at this scale is how gentle gravity appears despite its reach. Galaxies do not rush together. Clusters do not collapse violently. Motion is measured in millions of years per step. Yet given enough time, gravity produces order, hierarchy, and structure on the grandest scales imaginable. Gravitational interactions between galaxies also help test theories of gravity itself. By comparing lensing maps, galaxy motions, and simulations, astronomers check whether gravity behaves as expected across enormous distances. So far, general relativity has passed these tests with remarkable success, even at the scale of galaxy clusters. One famous example is the Bullet cluster, a system where two galaxy clusters have collided. Observations show that visible matter, primarily hot gas, has been slowed and displaced by the collision, while most of the mass inferred from gravitational lensing has passed through largely unaffected. This separation provides strong evidence that dark matter exists and interacts primarily through gravity. In this way, gravity between galaxies becomes a powerful investigative tool. It not only binds structures, but reveals their composition and history. Motion, distortion, and lensing all carry information about what lies beneath the visible surface of the universe. Despite the scale, the principles remain consistent. Mass curves spacetime. Curved spacetime guides motion. Whether dealing with a planet, a star, a galaxy, or a cluster of galaxies, gravity operates according to the same underlying rules. What changes is the scale and the timescale over which effects become apparent. Understanding gravity between galaxies completes the transition from local interactions to cosmic networks. Individual galaxies are no longer the focus. Instead, gravity is seen weaving them into larger systems, linking them across vast distances into a connected whole. This perspective reinforces the idea that the universe is not a collection of isolated islands. It is a continuous structure shaped by gravity at every level. Between galaxies, gravity is patient and far-reaching, binding the largest known systems without haste or forceful motion. Across intergalactic space, gravity quietly maintains the universe's architecture. It holds clusters together, traces unseen matter, and connects galaxies into a vast web that spans the observable cosmos. What appears empty between galaxies is, in fact, the stage on which gravity performs its most expansive work. The universe is expanding. This statement is simple to say, but it carries profound implications for how gravity operates on the largest possible scales. Space itself is stretching, increasing the distances between galaxies over time. This expansion is not something galaxies are moving through like debris in an explosion. It is a change in the structure of space-time itself. Within this expanding backdrop, gravity continues to act, shaping matter and influencing cosmic history. At first glance, expansion and gravity seem opposed. Expansion increases separation. Gravity pulls things together. Yet the universe contains both, operating simultaneously. Understanding how they interact requires stepping back from local motion and considering how space-time behaves as a whole. The expansion of the universe was first inferred from observations showing that distant galaxies are moving away from one another, with more distant galaxies receding faster. This relationship, now known as Hubble expansion, reflects a uniform stretching of space rather than motion through space. Every large-scale region sees the same pattern when viewed broadly enough. Gravity plays a crucial role in this picture. While space expands overall, gravity resists that expansion locally. Where matter is dense enough, gravity can overcome expansion and bind structures together. This is why galaxies, star systems, and clusters do not expand internally. The gravitational attraction between their components is strong enough to hold them together against the stretching of space. This balance explains why expansion becomes noticeable only at very large scales. Within a galaxy, gravity dominates. Between galaxies separated by millions of light years, expansion becomes significant. The two effects operate in different regimes, each relevant at its own scale. Cosmic expansion itself is not driven by gravity alone. Observations show that the expansion of the universe is accelerating rather than slowing down. This acceleration cannot be explained by visible matter or dark matter. Instead, it points to the presence of an additional component known as dark energy. Dark energy acts as a counteracting effect to gravity on the larger scales. It does not pull objects together. Instead, it influences the expansion of space itself, causing the rate of expansion to increase over time. Unlike gravity, which becomes stronger where mass is concentrated, dark energy appears to be distributed uniformly throughout space. The existence of dark energy was inferred from observations of distant supernovae, which appeared dimmer than expected, indicating faster expansion in the past. This conclusion has been supported by multiple lines of evidence, including measurements of the cosmic microwave background. The Planck mission, operated by the European Space Agency, provided some of the most precise measurements of the cosmic microwave background ever obtained. These measurements captured tiny temperature variations imprinted when the universe was only hundreds of thousands of years old. From these patterns, scientists inferred the composition and geometry of the universe. The Planck data indicate that the universe is composed primarily of dark energy, with smaller contributions from dark matter and ordinary matter. This balance determines how expansion and gravity have interacted across cosmic time. In the early universe, gravity dominated. Matter was denser. Expansion slowed as gravity pulled material together. Over time, as matter spread out, dark energy became more influential, leading to accelerated expansion. Despite this acceleration, gravity has never ceased to matter. It continues to shape structure wherever matter collects. Galaxies form because gravity overcomes expansion locally. Clusters form because gravity draws galaxies together along filaments of dark matter. Even as space expands, gravity sculpts matter into recognizable forms. This interplay explains the large-scale appearance of the universe. Expansion sets the overall framework, determining how distances grow. Gravity works within that framework, creating structure where it can. The result is a universe that expands globally while remaining richly structured locally. It is important to clarify what expansion does and does not do. Expansion does not tear apart bound systems. Atoms do not expand. Planets do not drift away from their stars. Galaxies do not stretch internally. Expansion affects space between distant, unbound systems, not the forces holding objects together. Gravity therefore remains the dominant influence wherever matter is sufficiently concentrated. Expansion becomes relevant only when gravitational attraction is weak by comparison. This distinction allows both processes to coexist without contradiction. From a relativistic perspective, gravity and expansion are both aspects of spacetime behavior. Gravity curves spacetime locally around mass and energy. Expansion describes how spacetime evolves globally. They are not separate mechanisms fighting each other. They are different expressions of the same underlying structure. This unified view helps resolve apparent tension between attraction and expansion. The universe does not choose between gravity and expansion. It exhibits both, each governing different scales and conditions. Over cosmic history, this balance has shifted. In the early universe, density was high. Gravity dominated, allowing small irregularities to grow into galaxies and clusters. As the universe expanded and thinned out, dark energy gained influence, accelerating expansion and limiting future structure formation. Even so, existing structures remain intact. Gravity continues to operate within them. Stars still orbit galactic centers. Galaxies still interact within clusters. Expansion changes the large-scale future, not the local present. Understanding gravity within an expanding universe places gravity into its final context. Gravity is not a force acting within a static backdrop. It is part of a dynamic spacetime that evolves over time. Its influence depends on scale, density, and cosmic era. This perspective also explains why gravity alone cannot determine the universe's fate. Gravity pulls inward. Dark energy pushes outward. The balance between them shapes cosmic evolution. Current observations indicate that expansion will continue to accelerate, gradually isolating gravitationally bound systems from one another. Yet even in such a future, gravity remains relevant. Within galaxies and clusters, motion continues. Time passes. Structures evolve. Expansion may separate regions, but it does not erase gravity's role within them. The expanding universe therefore does not diminish gravity's importance. It highlights it. Gravity is what gives structure meaning against a changing backdrop. It determines where matter gathers, how long systems persist, and how the universe organizes itself amid expansion. By integrating gravity into cosmic expansion, a more complete picture emerges. The universe is not simply flying apart, nor is it collapsing inward. It is doing both at once, depending on scale. Expansion sets the stage. Gravity writes the details. In this view, gravity is not overwhelmed by expansion. It is contextualized by it. Together, they describe a universe that evolves, stretches, and organizes itself according to deep and consistent principles. Gravity remains the thread that connects cosmic history, from the early dense universe to the structured present, and onward into an expanding future where space grows ever larger, but gravity continues to shape what remains within reach. At the largest scales, gravity reveals a universe that is neither random nor evenly spread. Matter is arranged in an intricate pattern of filaments, clusters, and vast empty regions that together form what is known as large-scale structure. This structure stretches across hundreds of millions of light-years and represents the cumulative work of gravity acting patiently since the earliest moments of cosmic history. These immense patterns are often called the cosmic web. Galaxies are not scattered uniformly through space. Instead, they trace long, thread-like filaments that intersect at dense nodes. Between these filaments lie enormous voids where very few galaxies reside. This arrangement is not accidental. It is the natural outcome of gravity amplifying tiny differences present in the early universe. Shortly after the Big Bang, matter was distributed almost evenly, but not perfectly so. Small fluctuations in density existed at the level of a few parts in 100,000. These slight variations were enough. Over time, gravity pulled more matter into regions that were already slightly denser than average. As matter accumulated, gravity strengthened, drawing in still more material. Regions that began slightly emptier lost matter to their surroundings and became progressively more vacant. This process unfolded over billions of years. Gravity did not act quickly or violently. It worked steadily, turning subtle irregularities into vast structures. Filaments grew longer and thicker, clusters formed where filaments crossed. Voids expanded as matter drained away. The universe gradually developed a visible architecture shaped almost entirely by gravity. Cosmic filaments themselves are enormous. They can span hundreds of millions of light-years and contain countless galaxies along their lengths. These filaments act as gravitational highways, guiding matter toward denser regions. Gas flows along them. Galaxies migrate slowly toward nodes where clusters reside. Gravity provides direction without urgency. At the intersections of filaments, gravity is strongest. These regions host galaxy clusters, the most massive gravitationally bound structures in the universe. Their growth is fed continuously by matter streaming in along filaments. Over time, clusters grow larger, drawing in galaxies and gas from their surroundings. Large-scale structure did not emerge by chance. It follows directly from the way gravity behaves in an expanding universe filled with matter and dark matter. Dark matter, in particular, plays a crucial role. Because it does not interact with light or radiation, dark matter began clumping earlier than ordinary matter. Its gravitational pull created the initial scaffolding on which visible structure later formed. As ordinary matter cooled and slowed, it fell into the gravitational wells created by dark matter. Gas accumulated, stars formed, galaxies emerged. The visible universe traces the deeper invisible framework laid down by gravity acting on dark matter. What is seen through telescopes represents only the illuminated edges of a much larger structure. This picture is supported by detailed simulations of structure formation. Using supercomputers, scientists model the evolution of the universe from early density fluctuations to the present day. These simulations incorporate known physics, including gravity, cosmic expansion, and the properties of dark matter. When run forward in time, they produce filamentary networks that closely resemble the observed universe. Projects such as the Millennium Simulation and later large-scale cosmological models demonstrate how gravity alone, given the right initial conditions, can generate the cosmic web. The agreement between simulation and observation is striking. Filaments, clusters, and voids emerge naturally, without requiring additional organizing forces. These simulations also reveal the timescales involved. Large-scale structure forms slowly. Individual galaxies evolve over billions of years. Filaments persist even longer. Gravity works across immense spans of time, shaping the universe gradually rather than abruptly. Nothing at this scale happens quickly. What is especially notable is that gravity produces order without design. There is no blueprint guiding matter into filaments. The structure emerges because gravity amplifies small differences repeatedly and consistently. The result is a universe that is structured but not rigid, patterned but not symmetrical. Even at the larger scales, gravity does not act alone. Cosmic expansion continues in the background, stretching space as gravity pulls matter together locally. The balance between these effects determines how structures grow and when they stop growing. In the distant future, accelerated expansion may slow the formation of new, large-scale structures, but existing ones will remain. Large-scale gravity also influences how information travels. Light from distant galaxies follows paths shaped by the gravitational landscape it crosses. Filaments and clusters bend spacetime, subtly altering the trajectories of photons. This gravitational lensing provides another way to map the universe's structure and confirm the presence of mass where little light is seen. From this vantage point, gravity becomes an architect rather than a force. It designs no shapes deliberately. yet it produces a universe with clear organization. It links the smallest early fluctuations to the grandest visible patterns. It connects the universe's origin to its present form through continuous influence. The scale involved is difficult to grasp. The distance between major structures is measured in hundreds of millions of light-years. The timescales span most of cosmic history. Gravity operates so slowly and over such vast distances that its effects are invisible on human timescales, yet undeniable when viewed across the full age of the universe. This perspective completes the outward expansion of scale. Gravity began as a familiar pull underfoot. It became a guide for motion, a shaper of stars, a binder of galaxies, and finally an organizer of the universe itself. At each step, the same principles applied. Only the scale changed. Seeing gravity at the larger scales also reframes emptiness. Voids are not failures of structure. They are part of it. They exist because gravity has moved matter elsewhere. Even absence carries the signature of gravitational action. The universe's large-scale structure stands as a record of gravity's long patience. Nothing rushed, nothing was imposed suddenly. Over billions of years, gravity transformed slight unevenness into vast order. It did so quietly, persistently, and without interruption. In this sense, gravity is not just something that acts within the universe, it is something that has shaped the universe's very form. The cosmic web is gravity made visible, written across space itself. At the larger scales, gravity shows what it has always been doing. It takes what exists, amplifies differences, and allows structure to emerge naturally. From near uniformity to intricate architecture, gravity remains the guiding influence, patiently shaping the universe into the form observed today. At the smallest scales, gravity becomes strangely quiet. The familiar descriptions that work so well for planets, stars, and galaxies begin to lose their clarity. This is not because gravity disappears, but because the tools used to describe it no longer fit comfortably alongside the rest of modern physics. At these scales, gravity meets quantum mechanics, and the two do not yet speak the same language. Quantum mechanics is the framework that describes how nature behaves at very small sizes. It governs atoms, particles, and the forces that act between them. Its predictions are extraordinarily accurate. Technologies such as semiconductors, lasers, and atomic clocks rely on it every day. Gravity, by contrast, is described with equal precision by general relativity, but only at larger scales. Each theory works remarkably well in its own domain. The difficulty arises when both are needed at the same time. In extreme situations, such as the very early universe, or the deep interior of black holes, gravity and quantum effect should both be important. General relativity treats space-time as smooth and continuous. Quantum mechanics treats reality as discrete and probabilistic. When these descriptions are applied together, mathematical inconsistencies appear. The theories resist being combined. This unresolved tension has led physicists to search for a theory of quantum gravity, a framework that would describe gravity using quantum principles. Such a theory does not yet exist in a complete, experimentally verified form. What exists instead are several competing ideas, each attempting to bridge the gap in a different way. One approach is known as loop quantum gravity. This framework suggests that spacetime itself has a granular structure at extremely small scales. Rather than being smooth, space may be composed of tiny loops or networks woven together. In this view, gravity emerges from the way these fundamental units connect and evolve. Time and space become quantized, much like energy levels in an atom. Another major approach is string theory. In string theory, the fundamental components of nature are not point-like particles, but tiny vibrating strings. Different vibration patterns correspond to different particles. Gravity appears naturally in this framework as a particular mode of vibration associated with a particle known as the graviton. String theory requires additional spatial dimensions beyond the familiar three, tightly compacted and hidden from direct observation. Both approaches are mathematically sophisticated and internally consistent, yet neither has been confirmed by experiment. The scales at which quantum gravity effects would become obvious are far beyond current experimental reach. Energies required to probe them directly are vastly higher than anything achievable with present technology. This is part of what makes gravity at the smallest scales so elusive. Gravity is extraordinarily weak compared to other fundamental interactions. At the level of particles, its effects are overwhelmed by electromagnetic and nuclear forces. Detecting quantum behavior of gravity directly is therefore extremely challenging. Despite this, gravity cannot be ignored at small scales. Questions about the origin of spacetime, the nature of singularities, and the earliest moments after the Big Bang all require an understanding of gravity under quantum conditions. Without such a theory, these questions remain partially unanswered. It is important to be clear about what is known and what is not. There is no experimental evidence yet that confirms how gravity behaves at the smallest possible scales. There is no agreement on whether space-time is continuous or discrete at that level. There is no confirmed particle that carries gravitational interaction in the way photons carry electromagnetic interaction. What is known is that current theories are incomplete in this regime. General relativity predicts singularities where curvature becomes infinite, such as at the center of black holes. Quantum mechanics suggests that infinities of this kind signal a breakdown of the theory rather than a physical reality. Reconciling these viewpoints remains one of the central challenges of theoretical physics. Researchers continue to explore indirect ways of testing ideas about quantum gravity. Observations of black holes, gravitational waves, and the cosmic microwave background may offer clues. Subtle patterns in these phenomena could hint at underlying quantum structure. So far, no definitive evidence has emerged, but the search continues. This uncertainty contrasts sharply with gravity at large scales. There, gravity is understood, measured, and confirmed with extraordinary precision. Predictions of general relativity match observation across galaxies and clusters. The theory works beautifully where spacetime curvature is gentle and quantum effects are negligible. At small scales, certainty fades. Gravity becomes a question rather than an answer. This does not represent failure, but honesty. Physics advances by recognizing the boundaries of its understanding. Gravity at the smallest scales marks one of those boundaries. The absence of a complete theory does not diminish gravity's role. Instead, it highlights how fundamental gravity truly is. It resists simplification. It connects geometry, motion, time, and structure in ways that remain only partially understood. There is also a quiet symmetry in this uncertainty. Gravity was the first force to be described mathematically, and it remains the last to be fully integrated into the quantum picture. The force that shapes the largest structures in the universe also defines the limits of current knowledge at the smallest scales. For now, gravity at the smallest scales remains an open question. Multiple ideas exist. None are confirmed. What is clear is that a deeper understanding of gravity will require new concepts, new mathematics, and new ways of testing nature. This uncertainty does not undermine what is known elsewhere. gravity behaves predictably across planets, stars, galaxies, and the universe as a whole. The mystery lies only at the extremes, where existing theories overlap. By acknowledging this limit, gravity takes on a different character. It becomes not only a force or a geometric effect, but a guide to what remains unknown. It marks the boundary between confident description and ongoing exploration. At the smallest scales, gravity reminds us that understanding is incomplete. The universe still holds layers of structure beyond present reach. What has been learned so far works remarkably well. What remains unresolved points toward future discovery. In this way, gravity at the smallest scales does not close the story. It leaves it open, quietly indicating that even the most familiar features of the universe still have depths yet to be understood. Gravity feels consistent because the human body was shaped within a very narrow gravitational range and has never known anything else. From the first moments of development, gravity is present as a constant background condition. Muscles form against it. Bones grow under its load. Balance systems calibrate themselves in response to it. By the time conscious awareness develops, gravity is already embedded so deeply into perception that it no longer registers as a separate influence. On Earth, gravity is remarkably stable on human timescales. The planet's mass does not change in any meaningful way from day to day. Its radius remains constant. Rotation introduces small variations, but these are subtle and predictable. The result is a gravitational environment that changes so slowly and so slightly that it appears fixed. What feels like a universal constant is, in reality, a local condition that remains steady enough to fade from notice. Human sensory systems are designed to detect change rather than constancy. Sudden shifts in acceleration are noticed immediately. A stumble, a fall, or a jump activates reflexes and attention. Steady downward pull does not. Gravity is always there, always the same within local experience, and so it becomes invisible to perception. The brain treats it as a baseline rather than a signal. Evolution reinforces this effect. Over millions of years, organisms that developed on Earth adapted specifically to Earth's gravity. Body plans reflect this adaptation. Limbs are proportioned to support weight efficiently. Circulatory systems are designed to move blood upward against gravity. Skeletal structures resist compression caused by constant load. Even cellular processes respond to mechanical stress shaped by gravity. Because every generation experienced nearly identical gravitational conditions, there was no selective pressure to detect subtle variations. Noticing a tiny change in gravitational strength offers no survival advantage when those changes are smaller than other environmental fluctuations. As a result, perception evolved to ignore gravity's fine details and respond only to large deviations. This explains why small variations in gravity across Earth go unnoticed. Gravity is slightly weaker at the equator than at the poles. It is marginally weaker at higher altitude than at sea level. These differences are real and measurable, but they are far below the threshold of conscious sensation. The body adjusts automatically without awareness. The vestibular system in the inner ear plays a key role here. It senses acceleration and orientation, helping maintain balance. It does not measure gravity directly. Instead, it detects changes in motion relative to gravity. When standing still, the system receives no new information. Gravity is present, but it provides no changing input to register. The same is true for muscles and joints. They respond to force and load, but once those forces remain constant, feedback stabilizes. the sensation of weight becomes the default condition rather than a stimulus. Only when weight changes abruptly, such as lifting an object or entering free fall, does gravity become noticeable. This creates the impression that gravity is absolute and unchanging. In practice, it is simply stable within the narrow window of lived experience. Outside that window, gravity varies widely. On the Moon, astronauts immediately noticed reduced gravity because it lay far outside Earth's familiar range. On Earth, the differences are too small to trigger the same response. Cognitive expectations also play a role. The brain builds predictive models of the world. Objects are expected to fall. Movement is expected to require effort. Balance is expected to behave in familiar ways. When these expectations are met, attention is minimal. When they are violated, awareness increases. Gravity on Earth rarely violates expectation. This consistency creates trust. Gravity becomes something that can be relied upon without thought. Chairs support weight. Floors remain beneath the feet. Objects behave predictably. This reliability allows attention to shift elsewhere, towards social interaction, problem solving, and environmental awareness. The result is a paradox. Gravity is one of the most influential forces in daily life, yet it is rarely considered. It shapes posture, movement, and health, but remains conceptually distant. It is experienced constantly but noticed almost never. Modern technology occasionally reveals gravity's subtlety. Precision instruments can measure changes caused by underground structures, tides, or passing celestial bodies. Atomic clocks reveal gravitational time dilation across small height differences. These measurements show that gravity is not perfectly uniform even locally. The body simply does not register those variations. Long-term exposure to altered gravity highlights how deeply adaptation runs. Astronauts returning from extended missions experience muscle loss, bone density reduction, and balance disturbances. These effects occur because the body adjusts to a different gravitational environment and then must readapt upon return. What felt constant was, in fact, a specific condition the body depended on. This underscores an important point. Gravity feels consistent not because it is universal, but because it is familiar. It is the condition under which perception evolved. Change reveals it. Stability hides it. Returning to Earth after exploring gravity across scales brings the experience full circle. After considering gravity inside stars, around black holes, across galaxies, and through the expanding universe, the everyday downward pull gains new context. It is no longer the default gravity of the universe. It is Earth's gravity. This does not make it less real or less important. It makes it specific. It belongs to this planet, at this mass, at this distance from its center. Life adapted to it because it was present, not because it was inevitable. Understanding why gravity feels consistent helps reconcile the familiar with the vast. The quiet steadiness underfoot is one expression of a broader phenomenon that behaves very differently elsewhere. What feels fixed is actually local. What feels universal is in fact contextual. Gravity feels consistent because it has been consistent here. The universe does not guarantee that consistency everywhere. Earth simply provides a narrow, stable gravitational environment that perception learned to treat as normal. Recognizing this does not disrupt daily life. Objects will still fall. Balance will still work, but it reframes experience. The constant downward pull is no longer just background. It becomes a reminder that even the most familiar aspects of reality are shaped by specific conditions. Gravity feels consistent because it has been quietly shaping bodies and minds for as long as they have existed. Its steadiness is not a law of perception, but a consequence of long exposure. What feels natural is not universal. It is local, learned, and deeply ingrained. By closing the loop back to human experience, gravity becomes both ordinary and remarkable. It is the same interaction that bends spacetime and binds galaxies, expressed here as a gentle, reliable pull. Familiar not because it is simple, but because it has always been there. Gravity appears to be a single, universal feature of the universe, and in a fundamental sense, it is. The same underlying interaction governs falling objects on Earth, the motion of planets, the structure of galaxies, and the evolution of the universe itself. Yet the way gravity is experienced, measured, and expressed depends strongly on where it is encountered. Gravity is universal in principle, but local in practice. Across every scale examined so far, gravity follows consistent rules. Mass and energy curve spacetime. Curved spacetime guides motion. This framework applies everywhere, from the surface of a small moon to the edge of a galaxy cluster. What changes is not the law, but the context. The amount of mass involved, how it is distributed, and the distances between objects all shape how gravity manifests. On Earth, gravity feels steady and familiar because the local conditions are stable. Earth's mass, radius, and internal structure produce a gravitational field that varies only slightly across the planet's surface. Human perception evolves within this narrow range, reinforcing the sense that gravity is fixed and uniform. In reality, even here, gravity changes subtly with altitude, latitude, and underlying geology. The changes are real, but small enough to go unnoticed without precise instruments. Move outward, and the variation becomes easier to see. On the Moon, gravity weakens noticeably. On Mars, it changes again. Around gas giants, it strengthens. These differences do not signal different kinds of gravity. They reflect the same interaction responding to different masses and sizes. The rule remains the same. The outcome shifts with circumstance. Inside stars, gravity operates not just at a surface, but throughout a volume of hot plasma. There it balances nuclear fusion, regulating stability and lifespan. In small bodies such as asteroids, gravity becomes so weak that structure is loose and fragile. Material barely holds together. These environments feel radically different, yet they arise from the same principles applied at different scales. As distance increases further, gravity no longer announces itself through weight or falling, but through motion over time. Orbits become the dominant expression. Stars circle galactic centers. Galaxies drift within clusters. Matter flows along filaments spanning hundreds of millions of light years. Gravity guides these motions patiently, often requiring millions or billions of years for its effects to become apparent. At the largest scales, gravity acts as an architect. It amplifies tiny variations left over from the early universe, shaping matter into the cosmic web. Filaments, clusters, and voids emerge not because gravity changes its nature, but because it is allowed to act over immense distances and long times. Structure arises gradually without design, through consistent influence. At the smallest scales, certainty fades. Gravity resists easy integration with quantum mechanics. While general relativity describes gravity with extraordinary accuracy at large scales, it does not yet align smoothly with quantum theory. This does not imply contradiction. It marks the boundary of current understanding. The same interaction that governs galaxies also defines when knowledge becomes incomplete. Seen together, these differences might appear to suggest multiple versions of gravity. In truth, They reveal a single interaction responding continuously to context. Gravity does not switch modes. It does not become something else near a black hole or fade into irrelevance in empty space. It expresses itself according to mass, distance, density, and scale. This continuity matters. It means that extreme environments do not invalidate familiar ones. The gravity near a neutron star does not contradict the gravity felt on Earth. It extends it. The quiet pull underfoot and the intense curvature near a black hole are connected by the same framework. One feels ordinary because it is local. The other feels extreme because it is distant in scale, not in principle. Understanding gravity as a local experience helps reconcile familiarity with strangeness. Earth's gravity is not the standard by which all gravity must be judged. It is one outcome among many. It feels central only because it is experienced constantly. In a universe filled with varied gravitational environments, no single location defines what gravity should feel like. This perspective also clarifies why gravity can appear both simple and profound. At human scales, gravity can be summarized easily. Objects fall, weight exists, motion requires effort. At cosmic scales, gravity shapes space-time, bends light, slows time, and reveals unseen matter. The simplicity of local experience does not capture the full depth of the interaction, but it does not misrepresent it either. Gravity's consistency lies in its rules, not its outcomes. The rules apply everywhere. The outcomes differ because the universe is not uniform. Mass is unevenly distributed. Distances vary. Structures form and dissolve. Gravity responds faithfully to what exists. This view avoids contradiction by embracing context. Gravity is not gentle in some places and violent in others because it changes its nature. It is gentle where mass is spread out and distances are large. It is intense where mass is concentrated. It is subtle where change is slow. It is dramatic where curvature becomes extreme. The same principle explains why gravity can be almost unnoticeable in daily life and yet dominate cosmic evolution. Local stability hides variation. Vast scale reveals it. Neither perspective is wrong. Each reflects a different slice of the same reality. By following gravity across environments, a coherent picture emerges. Gravity binds matter without rigidity. It guides motion without intention. It shapes structure without design. It does so continuously, from the smallest accessible scales to the largest observable ones. This continuity also lends gravity a quiet reliability. Even where understanding remains incomplete, gravity behaves consistently with what is already known. Uncertainty lies not in gravity's capriciousness, but in the limits of current theory. What is understood fits together smoothly across scales. Returning to the idea of gravity as a local experience places emphasis back on perspective. Every observer experiences gravity from somewhere. That experience reflects local conditions rather than universal norms. Earth's gravity feels ordinary because it is the condition under which perception developed. Elsewhere, gravity would feel different, but no less valid. Recognizing this does not diminish the everyday experience of gravity, it enriches it. The downward pull becomes one expression of a broader phenomenon that operates everywhere, shaping the universe in ways both subtle and immense. Gravity does not contradict itself as scale changes. It reveals more of itself. Each environment adds context rather than conflict. From gentle pressure beneath the feet to the slow motion of galaxies, gravity remains the same interaction, continuously expressed. Seen this way, gravity is not a single sensation or a single equation. It is a relationship between mass, space, time, and motion, that adapts naturally to circumstance. Local experiences fit within a universal framework. The familiar belongs comfortably alongside the vast. This understanding prepares the ground for reflection rather than resolution. Gravity does not demand a final summary. It invites perspective. It connects the immediate and the cosmic without forcing them to feel the same. In a universe filled with variation, gravity provides continuity. It operates everywhere, but always locally. It feels stable where conditions are stable. It feels strange where conditions are extreme. Neither experience defines gravity completely. Gravity is universal in its reach, local in its expression, and continuous across every scale explored so far. What changes is not gravity itself, but where it is encountered and how much of it is felt. That realization brings the journey to a calm pause. Gravity has been traced from the ground beneath the feet to the structure of the universe and back again, not as a collection of contradictions, but as a single interaction expressed differently across a varied cosmos. What remains is not confusion, but coherence. Gravity works everywhere. It simply does not work the same way everywhere. Gravity is often treated as something already known. It is taught early, experienced constantly, and relied upon without thought. Objects fall. Weight exists. Motion requires effort. These facts feel settled, almost complete, and in many important ways they are. Gravity is one of the best tested and most reliable features of the physical universe. At the scales most familiar to daily life, gravity behaves predictably. It holds bodies to the ground, keeps oceans in place, and governs the motion of the moon around Earth. Classical descriptions explain these behaviors with remarkable accuracy. Modern physics deepens that picture, showing gravity as the curvature of spacetime shaped by mass and energy. Together, these descriptions allow precise prediction across an enormous range of conditions. At larger scales, understanding remains strong. Gravity explains how planets orbit stars, how stars move within galaxies, and how galaxies assemble into clusters and filaments. Observations confirm these models again and again. Measurements of stellar motion, gravitational lensing, and cosmic structure all align with the same underlying framework. Gravity, as described by general relativity, continues to perform exactly as expected across the observable universe. Even where gravity reveals things that cannot be seen directly, such as dark matter, the logic remains consistent. Motion responds to mass. When motion cannot be explained by visible matter alone, additional mass is inferred. Gravity does not change its behavior. It exposes what is missing. In this way, gravity acts as both a force and a diagnostic, revealing the universe's hidden structure through careful observation. At the larger scales, gravity integrates naturally with cosmic expansion. It shapes structure where matter is dense and yields to expansion where matter is sparse. This balance explains why the universe can grow larger while remaining richly organized. Gravity still matters because it always matters locally, even as space itself stretches globally. At the smaller scales, however, understanding becomes incomplete. Gravity does not yet fit comfortably into the quantum description that governs particles and forces at very small sizes. Attempts to unify these frameworks continue, but no final theory has emerged. This gap does not undermine what is known elsewhere. It simply marks the edge of present understanding. It's important to distinguish between uncertainty and inconsistency. Gravity does not behave unpredictably at small scales. It behaves in ways that are not yet fully described. The absence of a complete quantum theory of gravity does not erase the success of existing theories where they apply. Instead, it points toward future refinement. Across this entire range, from human experience to cosmic structure, gravity remains continuous. There is no moment where one kind of gravity gives way to another. There are no contradictions between gentle and extreme environments. There is only scale. As mass increases, gravity intensifies. As distance grows, its effects spread out. As time extends, small influences accumulate into vast structures. Perspective is what makes gravity feel simple or profound. From the surface of Earth, gravity is steady and familiar. From orbit, it becomes motion guiding. Near a black hole, it becomes space-time curvature revealed. Across the universe, it becomes architecture. None of these views replace the others. They coexist, each accurate within its frame. Living inside one version of gravity means inhabiting a specific set of conditions. Earth's mass, size, and composition create a gravitational environment that feels natural because it is the only one experienced directly. Bodies evolved within it, senses calibrated to it, expectations formed around it. This does not make Earth's gravity typical, it makes it local. Elsewhere, gravity expresses itself differently. On small moons, it barely holds material together. Inside stars, it balances nuclear fire. Between galaxies, it guides motion across millions of light years. Near extreme objects, it reshapes time and space in ways that strain intuition. These differences are not evidence of inconsistency, they are evidence of reach. Understanding gravity through perspective reduces the need for final answers. Gravity does not resolve into a single sensation or description. It unfolds across context. What matters is not whether gravity is fully explained in every regime, but whether the explanations that exist align with observation and with each other. So far they do. There's a quiet reassurance in this. Gravity does not surprise without reason. When new phenomena appear, they emerge where conditions change, not where rules fail. The universe remains intelligible even where it remains incomplete. This perspective also allows calm acceptance of uncertainty. Some questions remain open. How gravity behaves at the smallest possible scales is not yet known. What happens at the deepest interiors of black holes remains beyond direct observation. These are not gaps to fear, they are boundaries marking where exploration continues. For everyday life, gravity remains exactly what it has always been. The ground supports weight. Movement feels familiar. Nothing learned about gravity elsewhere changes that experience. Instead, it places it within a larger context. The pull underfoot becomes one expression of a phenomenon that operates everywhere. That realization does not diminish the ordinary, it enriches it. The act of standing still becomes participation in a cosmic interaction. The sense of balance becomes alignment with space-time. The reliability of gravity becomes evidence of deep consistency rather than simplicity. Living inside one version of gravity means living inside one set of answers and one set of unknowns. It means experiencing gravity locally while understanding it globally. It means accepting that familiarity does not equal universality. From this perspective, gravity does not demand attention. It does not ask to be solved completely before it can be trusted. It simply operates, shaping motion, structure, and time wherever mass exists. The universe does not offer a single viewpoint from which gravity can be fully grasped. It offers many. Each adds clarity without cancelling the others. Together they form a picture that is coherent, expansive, and still open. What remains is not a final explanation, but orientation. Gravity places everything somewhere. It connects objects without contact, structures without design, and moments without pause. It provides a framework within which change unfolds calmly and predictably. Here, within Earth's steady pull, gravity feels quiet and dependable. Elsewhere, it feels different. That difference does not fragment understanding, it completes it. Gravity works everywhere. It simply does not feel the same everywhere, and living inside one version of it is enough to remain grounded, connected, and at ease within a universe shaped by the same influence from edge to edge.